Hey everyone, welcome to Rose Academy. In the last tutorial, we look at how to do some basic operations with complex numbers. And in this tutorial, we're going to start by looking at modulus of a complex number. Also in this tutorial, we're going to be looking at how to go with complex conjugate and how to perform some operations concerning complex conjugate. So now let's start with modulus of a complex number. Also, we can say that the modulus of a complex number is also the absolute value of the complex number. So we can say modulus, or we call it absolute value. Take note of these two things. Is that they call it the modulus or they call it the absolute value of a complex number. And we are used to complex number if you define a complex number z by x plus iy. We know that from the last tutorial that x is the real part, y is the imaginary part, and I is the imaginary number. So we define the complex modulus. So this is the modulus of z, that is the modulus of x plus iy. And this can be defined as the square root of s squared plus y squared. So this is how we define the modulus of a complex number. If you have a complex number z and we have to find the modulus, we simply take the square root of the squared of the real part plus the square root of plus the square of the imaginary part. So that's simply how we define the modulus or the absolute value of a complex number. Now let's look at some properties of absolute value. No, this is very important we note the properties of absolute value. If you have to do some operations concerning absolute value, we are going to need these properties. And the first one we are going to be looking at is this. If you have, let me define two complex numbers z1 and z2. So we are going to be considering these two complex numbers given z1 and z2. If you have the complex modulus of z1 multiplied by z2, so there's a multiplication sign between this. It's also the same as finding the modulus of z1 and multiplying by modulus of z2. I don't know if you understand this. If you have two complex numbers z1 and z2, you multiply the two of them and find the modulus. It's going to be the same as finding the modulus of each of them and multiplying the two together. For example, if you have z1, let me increase the size. If you have complex number z1, which is defined as 2 plus 3i, and we have z2, which is defined as 4 minus 5i. So if you find the modulus of z1 and also the modulus of z2 and multiply them together, it will be the same as multiplying z1 and z2 and finding their modulus. So that's the first property of modulus of a complex number. The second one is having addition in between the two. If you have z1 plus z2, so here we don't have equal to, but we have it's going to be less than or equal to the modulus of z1 plus the modulus of z2. Take note of this. If you have z1 plus z2 and find the modulus of the two of them, it's going to be less or equal to the modulus of z1 and adding it to the modulus of z2. So this is the second property of the third one. This is the second property of the modulus of a complex number. Now the third one is having subtraction in between the two. If you have z1 minus z2, you can do some examples to practice this. Just instead of z1 and z2, you can substitute z1 to be 2 plus 3i and z2 to be 4 minus 5i. And we're going to derive that what we are proving it's actually correct. If you have z1 minus z2, this is going to be greater than or equal to the modulus of z1 minus the modulus of z2. And this actually makes sense. If you have z1 minus z2 and we find the modulus of the two of them, it's going to be greater or equal to z1 minus z2. So that's the second property of modulus of a complex number. Now the fourth. So the fourth is when we consider division. If you have the modulus of z1 over z2, now we are taking the z1 over z2 and we are finding the modulus once. This is going to be equal to finding the modulus of one and dividing by the modulus of the other. So it's going to be equal to z1 over z2, finding the modulus of z1 divided by modulus of z2. And fifth, which is the last but not the least, if you have modulus of z and we square this, it's going to be equal to z multiplied by z conjugate. Now I know we have not introduced the term something like this. This refers to as the seed conjugate. It means we are going to look at that next. Just hold on. So if you have the modulus of z, a complex number, and we square it, it's going to be equal to z multiplied by the conjugate of z. So let me clean this. So we're going to be looking at complex conjugates now. So that's basically it concerning the modulus of a complex number. This is very easy to work with. For example, instead of working with z and z1, z2, if you substitute normal values, so if you have a z1 to be 2 plus 3i, I've just set for like maybe 2 of this, and z2 to be 4 minus 5i. So let's test if the property 1 is correct. Now I'm multiplying these two now, which is 2 plus 3i multiplied by 4 minus 5i. Let me change this to another column. So this is going to be equal to 2 multiplied by, let me write this out explicitly, 2 into brackets 4 minus 5i plus 3i into brackets 4 minus 5i. So multiplying this, we have 8 minus 10i plus 12i. This is going to be plus 15. Now how do I get plus a? If I multiply 3 and 5, I'm going to have minus 15. And don't forget to prove in the last tutorial that I square equal to minus 1. So minus 1 times 15, we have plus 15. So and here we have 8 plus 15. If I'm to use my calculator to calculate this, 8 plus 15, I have 23. And we have minus 10 plus 12, and this is plus 2 plus 2y. So we have the multiplication of z1 and z2 to be 23 plus 2i. Now I'm finding the modulus of this. I'm going to have modulus of 23 plus 2i. And how do we define modulus? To be the square root of 23 squared plus 2 squared. So by calculation, this is going to be equal to this is equal to root 533. You can take this to decimal if you like. So that let's keep that at one side, that we have z1 multiplied by z2 to be this. Now let's do this individually. Let's find the modulus of the complex numbers individually, and let's see whether we arrive at the same answer or not. So we have z1, modulus of z1, if you recall, z1 is 2 plus 3i, and this is equal to the root of 2 square plus 3 square, and this is equal to the square root of 13. So that is the modulus of z1. So z2, if you recall, is, let me go up and check that, 4 minus 5i. We have 4 minus 5i, and this is going to be this square root of 4 squared plus minus negative 5 squared, and this is going to be equal to, that is 16 plus 25. That is the root of 41. So if you multiply the root of the modulus of z1 multiplied by the modulus of z2, this is going to be root 13 multiplied by root 41, and this is equal to the root of 533, which is the same as what we got while calculating them together. So we have the same answer here. So that's just a proof of property 1. So you can carry on and prove property 2, 3, 4, and 5 yourself and tell us that they're actually true. So that's it for that concerning modulus of a complex number. Now let's look at the conjugate of a complex number. We are going to be looking at z bar. Let's see what this means by looking at the conjugate of a complex number. So now let's look at what we refer to as the complex conjugate. Complex conjugate. In the last tutorial, if you remember, when I was talking about division of complex number, I talked about realification of complex number. Let me make this more bold. Of complex number. Now, if you recall, I said that in SOD, why whenever we are considering division in sort, we term this as rationalization of sorts. So if you have a sort A over B, then we divide it by denominator, but we change the if the sign is negative, we change to positive. If it's positive, change to negative. So the same thing is applicable in complex numbers, and we call this the complex conjugate. Whenever we are performing a division that involves manipulating or using the complex conjugate, we term this as the realification of the complex number. Realification of the complex number. So this is what we are going to be basically looking at while we are looking about complex conjugate. So let's start by looking at complex conjugates. Let me delete this so we can have more area to work with. So now what do we define as the complex conjugate? So if you have z to be equal to x plus iy, which is a complex number, then the number z bar, which is the complex conjugate, equal to x minus iy. If you notice here that we change the positive sign here to negative sign. So the same thing applicable if you have z2 to be equal to x minus iy. If you have the complex conjugate, it's going to be x plus iy, and this is what we refer to as the complex conjugate. So we are going to be using this in realification of complex number and also in division, and also performs other operations that involves complex conjugate. So just like we look at the properties of modulus of complex number, we're also going to look at the properties of complex conjugate. And just like in the case of complex number, in the case of modulus that we have 5, in this case we're going to have 7 of them. But before I look at that, let's look at graphical representation of this. Let me change this to a more vibrant color. Now, how do we define complex conjugates in terms of the real graph, the real number and the complex number graph? If you have a graph, just like we have seen, these are x-axis and these are y-axis. But in the last video, I told you about real axis and the imaginary axis. So let's say we have this. So we have a complex number z, which equal to x plus iy. So if you are to graphically see how the complex conjugate behave, it's like mirroring this whole complex number towards the negative y-axis. So therefore we are like taking it down. So in this case you are going to have, we still have the same, if you study this very well, we still have the same x, but y has changed. So we now have minus y here, don't forget, and we have y here. So we have minus y and we have y, and don't forget this is our real axis and this is the imaginary axis. So the I is there. Let me put the I. So yeah, instead of having x plus iy, we are going to have x minus, since we are working the negative axis here. So this is the complex number and this is the complex conjugate. So we can just join this. So that's just how to graphically visualize what we refer to as the complex conjugate. Now let's go back to where we are coming from, which is the properties of complex conjugates. Now the first one is this, that if you have, I'm also going to be working with two complex numbers here, x1, z1 and z2. So if you have z1, take note of this, it's going to ease your work. If you have a good handle of the properties, you will not spend much time trying to do any work that involves complex conjugates. And we have to find the conjugate of this. It's going to be equal to find the conjugate of each the individual complex number and adding them z2 bar. So we have z1 plus z2. The complex conjugate is going to be equal to the complex conjugate of z1 plus the complex conjugate of z2. So that's the first one. The second one is if you are considering multiplication, we have z1, z2, and find the complex conjugate. This is going to be equal to also something like z1 over z2. This is actually like the same thing. It's no more, it's not much of a property. So the third one, if you have z to the power of n, and later we're going to look at how we can deal with work the complex number raising to a particular power. We're going to see how we can change complex number from the normal complex representation to polar representation, so we can easily work with, or changing them to exponential form, so we can easily work with raising them to a particular power. So if I have the complex conjugate of this, it's going to be equal to the complex conjugate of z to the power of n. So that's this is very important law. That's the third one. Now the fourth one. Now if I have like a double complex conjugate, something like z bar bar, this is the same as z. So we are like find the complex conjugate 2 times, it's still going to lead us back to z. Now the fifth one. This one I'm going to explain it more of a bit later. If you have z bar, this is going to be equal to a square plus b square. So how we work with this, we are going to see that later. So this isn't applicable the sixth, and maybe I'll just hold on with this for now. I'm going to introduce this later. So that's it concerning complex conjugates, the properties of complex conjugates. We look at the first, second, the third, and the fourth one. The fifth, sixth, and the seventh, we're going to be looking at them later. Now, I would like to look at some examples on complex conjugates. I won't test this just like I did for modulus. You can substitute value for z1, z2, and try to check if these laws are true. I'll just look at 3 examples that will combine both modulus and complex conjugates. So let's look at the first one. This will be like an exercise. Number 1. If you have z1 to be equal to 2 plus 3i and z2 to be equal to 4 minus 5i. So express the following. Let me write this. In the form of in the form x plus iy. And this is very important. Express whatever we are going to do, we have to express this in the form x plus iy. Now, this is the first expression. 5 multiplied by z1 plus 3 multiplied by z2 squared. And the second one is z1 over z2, and find the complex conjugate. Now, the first one, let me use A. We have 5z1 plus 3z2, everything squared. Now, let me start this one after the other. So we have 5z1, that is 5 multiplied by z1, that is where like scalar multiplying a complex number. Z5 into bracket 2 plus 3i. And if I'm multiplying by a real number, we just multiply both the real and the complex part by the real number. So this is 10 plus 15i. And the second part, which is 3z2, is going to be 3 into brackets. The z2 is 4 minus 5i. So this is 3 times 4 is 12 minus 15i. So we have this next thing is to find the addition, which is 5z1 plus 3z2. So this is 10 plus 15i, that's 5z1 plus 12 minus 15i, and that is 3z2. If you study here, we have that plus 15i minus 15i, they are going to cancel out, and we have 10 plus 12, which is 22. So we are not done. The next thing to find is to find the square of 5z1 plus 3z2 squared, and this is 22 squared. So if you complete this, we have 22 squared to be equal to 484. Now, we are not to leave our answer in this format. If you study this, we have said in the form x plus iy. And if you recall from last tutorial, I'll talk about purely real and purely imaginary complex number. Let me just remind you. If you have a complex number in the form of a plus 0i, this is purely real. And if you have a complex number in the form of 0 plus ai, and this is purely imaginary. So yeah, it's like we have a purely real number. You only have the real number 484. The imaginary part is not there. So this is a purely real complex number. Purely real complex number. So if you have to express it in the form of x plus iy now, it's going to be 484 plus 0i. 484 plus 0i. And I've expressed it in the form of a complex number. And this, don't forget, this is a purely real complex number. The same thing if you have 0 plus iy, this is purely imaginary. Just put 0 in the real parts to make it purely imaginary complex number. So the B part of our question, which is to find z1 over z2, and we have the complex conjugates. Let me see if I have a more area to work with. Now, saying that I don't have much area to work with, I'm going to clean off. Let me just go to the beginning. No, I'm going to clean this off so we have a more organized. And lastly, this. So let's go back to our question. B part, which is to find the complex conjugate of z1 divided by z2. Now the first thing we have to do is to divide z2 by z1. So okay, I don't need to write this again. So we have z1 to be equal to 2 plus 3i over z2 to be equal to 4 minus 5i. So just like I mentioned initially, what we have to do now is to do the realification of the complex number. We are making it real. So that is what we are going to do now. And just like in the case of sort, multiply this by the complex conjugate of the denominator. And the complex conjugate of the denominator is 4 plus 5i. Also 4 plus 5i. We check 4 plus 5i over 4 plus 5i is still 1. So we are doing nothing. So multiplying it by the complex conjugate of the denominator will not affect the structure of our complex number. So let's go on with this multiplication. We have 2 multiplied by 4, that is 8, plus 10i, plus 12i, and this will be minus 15. Divided by the same thing here, we have 4. 4 multiplied by 4 is 16, plus 20i, minus 20i, plus 25. And then we are going to have this cancelling out. So we have 8 minus 15 is minus 7, plus 22i over 16 plus 25 is 41. So having this, to express this in the form of x plus iy, let's just distribute 41 into 7 and 22. So we have negative 7 over 41 plus 22 over 41. And you have expressed it in the form a plus I y. So this is the answer to the B part of the question. Now just a key takeaway. This is some part of the question. It's just a key takeaway. If you have something like RE is bracket Z1, this is basically talking about the real part of Z1. And in this case, this is going to be 2O. I forgot, we are not done with question 1 yet. Oh. We are not done with the B part yet. I made a mistake. If you recall what we have to find, it's not only Z1 over Z2, but the complex conjugate of Z1 over Z2. And this is going to be Z1 over Z2. So finding complex conjugate, meaning turning this to negative, we have minus 7 over 41, minus 22 over 41 I. And this is the complex conjugate of Z1 over Z2. So as I was saying the other time, if you have, this is a key takeaway, if you have the real part of Z1, so what this means is the real part of Z1, in this case will be 2. So that's that concerning the complex conjugate. Thank you very much. In next tutorial, I'm going to be looking at the arguments or also the properties, what they call the amplitude of a complex number. We look at how to plot the complex number on a graph on the real axis. Also, next we're going to be looking at how to do polar representation of complex numbers. This is going to ease our work. If you can represent all these things in polar form, it's going to make the work very easy. So I'll see you in the next tutorial. Thanks very much for joining this tutorial, and see you in the next one. Thank you.